Brought to you by Thomas Allgaier and Frennis. This edition highlights key LinkedIn posts on electrification and battery technology in weeks 25 and 26. Frennis is a B2B market research company that supports automotive suppliers with building feature-by-feature competitive intelligence that shows exactly how their product stacks up against the competition. You can find more info in the description. So, usually when we talk about infrastructure, there's this expectation of simple binary mechanics.
Right, like old school plumbing.
Exactly. You turn the tap, water flows. You plug a device into a wall outlet, and electricity flows. It's clean, it's visible, and it's either, functionally working or it's completely broken.
Yeah, and I mean, it's a comforting mental model, right? We expect our modern infrastructure to just behave with the exact same predictable reliability as a century-old utility grid.
But the moment you step into the actual operational reality of next-generation mobility and electric vehicle charging in particular, that simple plumbing metaphor just falls apart entirely.
Oh, completely.
We're looking at a landscape that is just incredibly complex. It's this fragile ecosystem of competing software protocols, sensitive chemical architectures, and super vulnerable hardware.
Yeah, and I think our mission today for this deep dive is to figure out if the EV industry is actually building the robust infrastructure of the future, or if we're, just creating incredibly complex, fragile digital plumbing that is basically destined to break down.
That is the ultimate tension right now. So we've gone through the absolute sharpest insights shared across LinkedIn by mobility industry professionals during calendar weeks 25 and 26.
And honestly, the recurring theme isn't really about the raw technology anymore.
Right.
It's much more about the brutal friction of actually deploying that technology into the real world at scale.
Exactly. So we're bringing you a completely fluff-free analysis of the trends dominating this space right now.
Right.
We're talking charging reliability metrics, the bottleneck of heavy-duty fleet electrification, the thermal realities of battery-back fast charging, and the commercial puzzle of bidirectional energy.
Lots to cover. Where should we start?
Let's unpack the reliability issue first, because the focus for mobility professionals has distinctly shifted. I mean, nobody's just celebrating planting new chargers in the ground anymore.
No, not at all. The sheer panic now is centered around just keeping the existing ones operational.
Right, and the metrics we've traditionally relied on to measure that operational success, they're proving to be completely inadequate. Lucas Schreier shared a fantastic insight about this on LinkedIn.
Oh yeah, Lucas's post was great. He pointed out that focusing on technical uptime is just a totally flawed industry standard.
Yeah, because the network providers will boast a 99% uptime.
Right, but Lucas argues the industry desperately needs a user-centric metric instead. He calls it the charging success rate, or CSR.
Which honestly highlights a massive disconnect in how the hardware reports its own health. Because a charger can have a 99% technical uptime, meaning, its internal computer's running, the screen is on, and it's pinging the central server. But if the payment gateway suffers a latency spike, the driver gets nothing.
Exactly. Or if the digital handshake between the car's software and the charger just times out.
Right. From the network's perspective, the charger was totally up. But from the user's perspective, it was a complete and total failure. High technical availability simply does not equal a successful charge.
And that silent failure creates an absolutely unsustainable support burden. Because when that complex chain of power, electronics, and telecom routing and back-end software breaks down for even a millisecond, what happens? The driver inevitably calls customer support.
Yeah, and then you end up with human operators trying to troubleshoot incredibly dense software stacks over a phone call, which is a nightmare. But there is some good news here. Bradford Christ highlighted a post about how Electric Era is tackling this exact bottleneck.
Yeah, with their ChargeMate AI voice assistant.
Yes, because so many of these failures are just software timeouts or user errors on perfectly healthy hardware. This AI is now autonomously resolving over 80% of driver support calls.
That's a huge number.
I know, right? It's answering those calls and diagnosing the digital handshake issues in under 3 seconds.
Wow. It's a highly effective application of artificial intelligence. It basically acts as instant triage, resetting sessions, or clearing digital lockups without any human intervention.
Which is great.
It is, but while AI is patching over the software friction on the front end, there's a much darker operational reality emerging on the back end.
Uh-oh. What's happening there?
Well, Gagan Bad raised a pretty serious warning about cybersecurity in this space. He specifically noted that bad actors are figuring out how to remotely manipulate a charger's broadcasted status.
Wait, you mean like spoofing the network? tricking the app into showing an available charger is broken, or vice versa.
Exactly that. They are manipulating the back-end communication so a perfectly functional idle charger displays as faulted or busy on the public network maps.
That sounds like, well, digital vandalism, basically.
Yeah.
But the implications for routing are massive, right? If vehicle navigation systems and user apps think a station is dead, they just route cars away from it.
Exactly. So it doesn't just destroy customer trust, it actively starves the charging operator of revenue. Their functioning hardware is essentially cloaked from the public.
And restoring that trust is incredibly difficult. I mean, if you drive to a station with 5% battery left and the app lied to you, you are going to permanently avoid that network.
Oh, absolutely. But the threats aren't just digital either. Kate Kudoli highlighted a severe physical equivalent that's actually occurring in Italy right now.
Like physical vandalism. We've all seen reports of thieves cutting external charging cables to sell the raw copper.
Right, but she noted a highly organized wave of professional vandalism. These groups are actually bypassing the external cables entirely.
Wait, really? What are they targeting then?
They are breaking into the main cabinets to steal the expensive high-voltage power stacks right out of the ultra-fast chargers.
Oh, wow. Which is a completely different tier of crime. I mean, cutting a cable is basically a crime of opportunity. Extracting internal power stacks requires serious technical knowledge.
Yeah, and specialized tools, plus an understanding of high-voltage safety.
Right, they are targeting the core power electronics because they're far more valuable on the black market than just raw copper.
Exactly. And replacing an entire internal power stack can leave a fast charging station offline for months while they wait for supply chain replacements.
Okay, so let me push back a bit here. If we are layering all this complex software and AI to fix reliability, aren't we just introducing entirely new digital points of failure?
I mean, yes, technology is definitely a double-edged sword here, but it's totally necessary to scale. And the hardware companies are fighting back.
How so?
Well, at the Power2Drive event in Munich, Torsten Freitag showcased a new system from Keepa. They've actually integrated an AI-powered monitoring system directly into the hardware, designed specifically to predict and prevent physical theft.
That's fascinating. How does it even do that?
It monitors internal impedance and physical access vectors to detect a theft attempt before the components are actually removed.
It really seems like we are caught in an escalating arms race. And if public charging networks are struggling with this layered complexity, software timeouts, cyber spoofing, and professional physical dismantling, it perfectly explains the pivot we're seeing in the commercial logistics sector.
Oh, for sure. Heavy-duty truck fleets are looking at the vulnerability of public infrastructure and just deciding to build their own private walled gardens.
Exactly. But by moving to private depots, they are hitting an entirely different, incredibly rigid physical limitation.
Yeah, they are slamming right into the reality of grid physics. Konrad Eickhoff posted an incredibly grounded analysis about this exact fleet electrification bottleneck.
I read that. He pointed out that the barrier to electrifying logistics isn't the electric truck itself anymore, right?
Right. It's not the truck, and it's not even the battery technology inside the truck. The absolute bottleneck is the local grid connection.
And the math on this is just staggering. If a logistics company wants to electrify a fleet of, say, 50 to 100 long-haul trucks and charge them overnight at their depot, they need the localized power equivalent of a small town.
A literal small town, and you cannot simply call up the local utility provider and demand a small town's worth of power capacity by next quarter.
Right, they'd laugh you off the phone.
Exactly. The utility has to assess the substations, analyze grid inertia, and often lay brand new high-voltage transmission lines. Upgrading that grid connection takes months, and in many jurisdictions, years of permitting, not to mention millions in capital expenditure.
But commercial logistics operates on razor-thin margins and strict timelines. They literally cannot wait years for a utility upgrade.
No, they can't, which is why Matthias Speicher shared a brilliant stopgap solution for this exact friction point from DRIVE.
Oh, the mobile battery containers.
Yes. It's essentially a mobile, high-capacity battery container. You can drop this massive energy storage unit into an SME logistics yard using a standard roll-off truck.
So it just trickles power continuously from their existing weak grid connection all day and night, storing it up.
Exactly, which completely bypasses the need for an immediate utility upgrade. When the trucks return to the depot, the mobile battery dumps that stored energy into the vehicles at ultra-fast speeds.
That's an ingenious buffer.
Yeah.
It allows the fleet to launch their electric operations immediately while that massive multi-year utility permitting process happens in the background.
Yeah, it's brilliant.
But if you extrapolate that out, as Christoph Wade and Inna Wettstein-Schneigelberger noted from the Power 2 Drive floor, the very definition of a logistics site is completely changing.
How so?
Well, they pointed out that depots can no longer just be parking lots where you happen to plug in a truck. They're being forced to evolve into deeply integrated, intelligent energy hubs.
Right. They basically have to operate like localized microgrids.
Exactly. A modern depot must balance on-site solar generation, massive stationary battery storage, and incredibly intelligent load management software to ensure the trucks are charged without tripping the local utility breaker.
And if you want to understand what that looks like when it's fully realized at scale, Syed Hasib Hassan shared his visit to China's largest electric truck charging site in Baishuan.
Oh, I saw those numbers. The scale completely breaks the Western mental model.
It really does. We are talking about 126 dedicated heavy truck spots powered by over 51 megawatts of Huawei infrastructure.
51 megawatts concentrated in a single commercial footprint is just massive. That requires thermal management and energy routing on a truly industrial scale.
It does, but Hassan pointed out the underlying economics that actually justify it. High fleet density combined with highly predictable, repetitive routes.
And that is the key variable right there, because if those heavy trucks are just doing predictable 200 to 300 kilometer industrial loops like hauling material from a line to a port and coming right back, the utilization rate of those chargers is practically 247.
Right, and that high utilization amortizes the massive upfront capital expenditure of the 51 megawatt infrastructure.
And the broader market adoption just follows that infrastructure deployment. Roberto Diesel shared data showing China's heavy truck new energy vehicle penetration. The NEV rate recently hit 53.9% in a single month.
Wow. They are vastly exceeding their own 2030 government targets right now.
Over half of all new heavy trucks sold in a month being electric is just a violent speed of transition. But this brings us to a critical inflection point, I think.
What's that?
Well, if a massive centralized depot with 51 megawatts is the ideal, what happens to everyone else? For the thousands of locations where the grid simply cannot support that kind of localized draw and where utility upgrades are impossible, the industry has to deploy decentralized solutions.
Right. If you can't bring massive grid energy to the charger, you have to bring the battery to the energy.
Exactly. And this introduces our third theme, the major industry pivot toward battery energy storage systems, or BES, and next-gen cell tech.
Yeah, Sidney Malevsky highlighted Anura Kamal's architecture at Electric Fish, which takes this concept to its logical conclusion.
Decoupling from the grid entirely, right?
Exactly. They are building battery-buffered charging units that entirely decouple the ultra-fast charging speed from grid limitations. Like the depot solution, it draws a low, continuous load from a weak public grid.
Which actually strengthens local grid stability rather than stressing it with unpredictable, massive spikes when a car plugs in. The theory is practically flawless.
The theory is yes. But Jack C. provided a deeply sobering reality check from the field regarding these BAS units.
Yeah, the brutal reality of the hardware. He noted that these mobile and stationary battery systems are experiencing alarming failure rates. They're often breaking down after just a single summer of commercial operation.
Just one summer. And what caught my attention is that the root cause isn't even just a high ambient temperature on a hot summer day.
Oh, interesting. What is the real killer then?
The ambient temperature is actually manageable. The silent killer of these massive storage systems is internal temperature differentials.
Ah, the gap between cells.
Right. A dashboard might show an average battery pack temperature that looks perfectly safe. But inside that massive physical enclosure, if there is an 8 to 10 degrees Celsius temperature gap between the cells on the hot outer edge and the cells trapped in the cooler center, the chemistry destabilizes.
Because a hotter lithium-ion cell has lower internal resistance, so it charges faster and degrades significantly faster than a colder neighboring cell in the exact same path.
Exactly. And that thermal imbalance creates voltage drift, which eventually forces the battery management system to trigger a sudden protective shutdown.
Wow. So this thermal reality is basically forcing the industry into a highly expensive engineering pivot.
Cheap, ambient air cooling systems are proving totally inadequate for high-cycle commercial BES units.
Yeah, manufacturers are having to re-engineer these massive containers with complex liquid cooling channels just to maintain tight thermal uniformity across thousands of cells. Which really raises a fundamental issue about the sheer chemical violence we are subjecting these cells to. I mean, we expect these batteries to sit in baking parking lots, absorb continuous trickle charges, and then instantly dump massive amounts of fast-charging current into vehicles.
It is a brutal operating environment, which perfectly explains why the race to commercialize next-generation chemistry is so frantic right now.
Everyone wants a more resilient cell. And Adam Bernard highlighted a major milestone here, noting that Stellantis and Factorial are successfully testing solid-state batteries on public roads in a Dodge Charger Daytona.
Yeah, and they are hitting an energy density of 375 watt-hours per kilogram.
375 watt-hours per kilogram is a transformational leap over current commercial lithium-ion cells. I mean, it alters the fundamental physics of the vehicle. Automakers can either drastically increase the range or significantly shrink the battery pack, stripping hundreds of pounds out of the vehicle's weight.
True. But as Klaus Ridloff pointed out, the real war for solid-state dominance has moved entirely out of the chemistry lab.
Right. Hitting 375 in a controlled lab test is great, but the actual bottleneck is the brutal mechanical engineering required to mass produce them.
The manufacturing trade-offs are severe. To build a solid-state battery, you replace the liquid electrolyte with a solid material, generally choosing between two pathways, sulfides or oxides.
And both have huge drawbacks, right?
Yeah. Sulfides offer phenomenal ionic conductivity, meaning they charge incredibly fast, but they are chemically reactive. The moment a sulfide electrolyte is exposed to ambient humidity in a manufacturing plant, it reacts to generate hydrogen sulfide gas.
Wait, toxic gas?
Highly toxic.
Wow. So if the material creates toxic gas when it touches normal air, you can't just retrofit an existing battery plant. You'd have to build massive ultra-dry clean rooms with extreme dehumidification systems.
Exactly. And the capital expenditure required just to maintain that factory environment would completely destroy the profit margins on the cells. So the industry must be looking at the alternative to avoid that toxicity.
Right, which brings us to oxide electrolytes.
Yep. They are chemically stable and totally safe to process in normal factory air. But they possess a fatal mechanical flaw. They are inherently ceramic.
So think about the brittle nature of a ceramic plate. Now imagine trying to process micrometer-thin sheets of that ceramic through high-speed roll-to-roll manufacturing equipment.
It would just shatter. You would end up with catastrophic microcracking across the entire production line.
So the winner of the solid-state race isn't the company with the best theoretical chemistry at all. It's the company that figures out the mechanical engineering to process brittle ceramics at high speeds, or the chemical engineering to stabilize sulfides without requiring billion-dollar dry rooms.
It is a profound manufacturing bottleneck. But, while the industry wrestles with the complexities of manufacturing massive industrial batteries and next-gen solid-state cells, there is an entirely different energy resource being largely ignored.
Oh, you mean the millions of highly advanced, perfectly functional batteries currently sitting idle in residential driveways?
Exactly. Which transitions us perfectly to our final theme, bidirectional charging, specifically vehicle-to-home and vehicle-to-grid, or V2G.
Yeah, we are finally seeing major automotive players pivot from treating the EV as just a car to treating it as a mobile energy asset. Michael Greenberg highlighted that BMW just hit their 2 millionth EV milestone, but they paired that announcement with a strategic pivot into vehicle-to-home integration.
Shifting the value from the car itself to the software orchestrating the energy.
Precisely. And the economic incentives for this orchestration are becoming too large to ignore. Farazi mapped out the commercial mathematics for UK fleets utilizing V2G.
Oh, the revenue stacking, right.
Yeah, by stacking different revenue streams, like buying cheap off-peak power, avoiding expensive peak energy tariffs, and providing frequency response back to the grid. A fleet operator can yield between 300 to 400 pounds per vehicle per year.
That is massive. And I actually want to break down that frequency response aspect for a second because it's vital. The power grid has to maintain a very strict frequency to remain stable. When millions of people increase their power usage simultaneously, demand spikes and the grid frequency physically sags. Traditionally, utility companies pay a fortune to keep fossil fuel peaker plants on standby to fire up and stabilize that demand.
But a parked, plugged-in EV fleet can accomplish the exact same thing.
And they can do it in milliseconds. The utility can digitally request a 30-second burst of energy from thousands of plugged-in delivery vans simultaneously.
So the vehicles act as a massive distributed shock absorber for the grid. They inject just enough power to stabilize the frequency without the utility ever needing to fire up a gas plant.
Exactly. And the fleet owner gets paid a premium for providing that instant responsiveness.
So if you multiply 400 pounds by a fleet of 500 delivery vans, you are generating massive secondary revenue while the trucks are literally just parked overnight.
Yeah, it's a huge opportunity.
So if the math works so beautifully, why isn't V2G deployed everywhere? Ali Abdelatif made a sharp observation walking the floor at Power2 Drive. He physically counted 17 different V2G-ready chargers on display from various manufacturers.
Right, the engineering is done, the hardware is solved, and literally sitting on the shelf.
Exactly. The hardware is no longer the friction point. The bottlenecks are now entirely regulatory and commercial. Grid operators are largely unprepared to handle decentralized energy injection at scale.
And we still lack unified standards, plus most consumer utility tariffs just don't actively reward users for providing that energy flexibility yet.
Which brings up a brilliant critique by Gregor Eckhart regarding the software dynamics at play here. He pointed out a massive contradiction in how the industry approaches standardization.
Oh, the open standards versus closed ecosystems debate.
Right. Everyone champions open standards for the foundational communication layers. For example, ISO 15118 is the underlying digital handshake that allows any brand of car to negotiate power delivery directly with any brand of charger.
Right, it acts as a universal translator, ensuring interoperability at the hardware level, which commoditizes the physical connection and drives down costs.
But, as Eckhart noted, the commercial optimization layer, like the application software that actually trades the energy and captures that 400 pounds of value, is being aggressively locked down into proprietary bundles.
It's so frustrating.
It's like buying a universal TV remote that can technically connect to any television in the world. But the manufacturer forces you to use their proprietary clunky subscription-based app just to change the volume.
That is a perfect analogy. It is a classic technology land grab. Standardize the low-margin hardware so adoption scales quickly, but monopolize the software interface where all the high-margin revenue is actually generated.
Exactly. But despite these commercial turf wars, we are finally seeing real consumer deployment. Giovanni Palazzo recently presented the Volkswagen Group's first actual V2G customer offer through Ellie.
So bidirectional energy is finally moving out of the pilot phase and into consumer driveways.
It's an incredible shift in how we interact with energy. But I know you have a final provocative thought on this entire transition that reframes a lot of what we've discussed today.
I do, yeah. It comes from Matthias Wietscher's keynote at the Munich Charging Night, and it challenges a core assumption of the entire energy transition.
Let's hear it.
Well, the business models for vehicle-to-grid and massive commercial battery storage all rely on the assumption that energy flexibility, the ability to store cheap power and discharge it when demand is high, will remain a highly valuable service.
Right, that's the whole business case.
But Wietscher poses a fascinating counter-scenario. What if battery deployments scale so rapidly across millions of cars and homes that energy flexibility becomes a completely oversupplied mass commodity?
Oh, wow. That completely inverts the economics. If every single driveway and commercial depot has massive battery storage, the grid will never experience those dramatic peaks in demand.
Exactly. And if there are no peaks, nobody's going to pay you a premium for your stored energy. The premium relies entirely on scarcity. If flexibility is everywhere, its market value approaches zero.
That is a wild thought.
But he raised an even more disruptive point regarding the physical infrastructure itself. We are currently spending billions of dollars globally to deploy manual charging stations.
Right, cables that require a human being to physically extract them and plug them into a port.
Yes. So as the automotive industry rapidly advances toward fully autonomous vehicles, a glaring physical bottleneck emerges.
Wait, I see where you're going with this. When a self-driving fleet returns to a depot with no human drivers, who is going to physically plug in the heavy liquid-cooled cables?
Exactly. We are pouring immense capital into infrastructure that requires manual human intervention. Are we building a global charging network today that will be rendered physically obsolete on day one of the autonomous era?
That is a phenomenal question for you to mull over. We might literally be building the world's most advanced, expensive, and thoroughly monitored plumbing system for a society that is about to stop using pipes entirely. If you enjoyed this episode, new episodes drop every 2 weeks. Also check out our other editions on future mobility and market evolution, next-gen vehicle intelligence, and commercial fleet insights. Thank you so much for joining us as we untangle this incredibly complex ecosystem. Keep questioning the infrastructure around you, and don't forget to subscribe so you never miss a deep dive. Catch you next time.